Hello, and thank you for attending our webinar on zero valent iron applications, nano, powder, or aggregate. Which do you need and which should you avoid? My name is Lowell Kessel. I'm a licensed geologist with academic training in geochemistry, hydrogeology, and environmental engineering, as well as professional experience for approaching 20 years in the field of geotechnical, hydrogeologic, and environmental engineering in the US, Australia, Brazil, and other Central and South American countries for about 10 years, and started working in China within the last couple of years. I'm the general manager and technical director for Ceres Corporation, which is a chemical company focused on sustainable remediation solutions for environmental contaminants in soil, groundwater, and surface water. Ceres Corporation is a division of Envirologic Inc., which is an international technology transfer and distribution representation company. Ceres has 4 primary products available commercially and in the development phase for others to address specific unmet needs in the global market. Metals treatment solution was the founding technology that launched Ceres into the market in 2015. Our product development experts have more than 50 years of collective experience in engineered chemical and biological solutions for cleaning soil, groundwater, and the environment from industry and academia. We strive to engineer and produce top quality and some of the best performing products available today, while remaining very aware of the economics in order to ensure the highest value in the industry. We're constantly re-engineering and improving our manufacturing processes and options to ensure high value. This presentation will focus on zero valent iron and its use for in-situ chemical reduction applications. We do have production and distribution globally. We produce in North America, Asia, and South America, while working with globally trusted and successful Fortune 500 chemical distribution companies to ensure safe and quality product delivery internationally. The presentation outline is really focused on a kind of a ZVI 101. So if you're looking for a more advanced level discussion, I think there's going to be some components and information here, references that you could use. But it's really, this presentation is really intended to set the foundation, and then there will likely be a ZVI 102 type presentation later this year. And I'll have a little bit more about that later. So we'll talk a little bit about the history of ZVI and in-situ chemical reduction, some of the processes and characteristics, design considerations, some information about product options and differences, and then follow up with conclusion, questions and answers, and concluding. So some history. With so much activity in the present, it is easy to overlook how much relevant work was done earlier. For example, the electrolytic deposition of dissolved metals onto zero valent iron metals has long been known to chemists, and the potential for application of this chemistry to water treatment was recognized in the 60s. Similarly, the use of zero valent iron metals to perform selective reductions for organic synthesis was already well documented since the 20s, and environmental applications had been described since the 80s. And in fact, prior to 1990, there had already been several fairly detailed process level studies on the removal of organics and inorganics. That early work was widely dispersed. However, a unified understanding of the processes responsible for contaminant removal by zero valent metals continues to take shape as we research and test new applications, specifically with regards to in-situ remediation by injection and PRB applications. Yet even in the last 10 years, there have been a wave of case studies bench studies and other publications discussing the various ways in which iron is necessary for in-situ chemical reduction on its own or in combination with other materials to target a wide variety of contaminants. And other materials is pretty broad now. There's a lot of different things that it can be combined with and is combined with for different applications. So what is in-situ chemical reduction? Well, chemical reduction adds electrons to the contaminant. And you can see an illustration here. And chemical oxidation, on the other hand, removes electrons from the contaminant. And in-situ chemical reduction involves transfer of electrons to contaminants from reduced metals like zero valent iron and reduced minerals. In-situ chemical reduction combined with biostimulation can be very valuable because chemical reduction of CBOCs occurs via abiotic as well as biotic pathways and can occur simultaneously. So combined methods offer synergies and sometimes cost and or technical advantages. Some aquifers are well suited to support chemical reduction. Abiotic monitored natural attenuation is contaminant degradation that occurs by direct reaction with ferrous iron or iron sulfide minerals. In-situ redox manipulation involves injection of dithionite into the subsurface to reduce native ferric iron to absorb the structural ferrous iron, which can in turn reduce contaminants such as chlorinated solvents, chromate, and tetrachloride, carbon tetrachloride. Biogeochemical reductive dechlorination, otherwise known as BIRD, is abiotic reduction of chlorinated solvents forming reactive iron sulfides. And those iron sulfides are created by stimulating microbial sulfate reduction in the presence of iron. And this process requires carbon source, sulfate, and iron. And the implementation of that is not necessarily add all of those things. It's to find out what may be deficient and then adding only those components. And that's more of an engineered approach, site-specific engineered approach. Now, engineered in-situ chemical reduction amendments are ones that combine the reductants and the necessary components, and some examples include, ultrafine iron powder with carboxymethylcellulose, or the Zeloy micrometal product with an emulsified vegetable oil, or various combinations of those are similar. Now let's review all of these different ways of applying in-situ chemical reduction. This chart from Paul Tratniak and others from 2014 is actually very useful to show the different aspects or implications as well as goal setting or limitations determination. Starting out with the most basic, are you treating a source or a plume? What is the method for installation? Are you looking at PRBs, mechanical mixing, or injection wells? And then how do you plan to implement? What are the necessary components? And that really depends on your conceptual site model. I think most remediation practitioners will always stress the importance of a very detailed conceptual site model that includes not just the geology and hydrogeology as well as contaminant distribution, but also includes geochemical analysis and understanding of the redox conditions and potential drivers or limitations. So this here shows at the top of the chart some of the different materials that might be added, and then reductant strength, basically engineered versus natural options. And so it gives you a good layout. Now it's modified from its original, not really in the sense of the raw material components, just but in the sense that the amount of iron one might use from a mechanical mixing to PRB to injection was relevant and dependent on the objectives of the site. Because you could use ZVI with or without EVO in any number of applications related to plume and or source treatment. And it really depends on the geometry. So it's not just a black and white, this is what you use under this chart. So this chart's very useful, it's illustrative, it has a lot of value, but there is a lot of variability in implementation, design, and the overall approach and how you might use it. And well, we've worked with numerous clients and projects from mixing to PRBs and injection, and the type of iron, the amount of iron, and relative contribution of supplemental organic substrate to further the combined biostimulation approach shows that it's quite variable, and it covers the whole spectrum. But I don't want to blur out everything here, so I made it into two different sections. And I think you noticed that the acronyms are here, so you can refer back to the acronyms for those items on the chart. So ZVI provides a source of divalent iron to promote indirect chemical reduction of chlorinated volatile organic compounds. And this is through beta elimination as well as hydrogenolysis. These are the two primary mechanisms. Now, it is anticipated that the majority of the work using ZVI is going to revolve around beta elimination, and that's, generally speaking, you might expect 90% or more of the work being done that way. However, hydrogenolysis does occur, and this is important consideration, because you might see short-term accumulation of DCE and vinyl chloride, which may be indicative of a predominant hydrogenolysis pathway, or it might be that that's just how things are getting going based on the injection approach, geometry, and equipment. So those are things to consider. Also important to consider is sulfide generation, which may be a result of high sulfate. There's also concern for nitrate organic carbon conditions, which may cause specific kinds of problems. The general stoichiometry of ZVI dechlorination is one where you have a number of different ways of the process. So one is reduction at the metal surface. The other is oxidation, where you're changing iron 2 to iron 3, or hydrogen gas generation. The reaction of zero valent iron with dissolved oxygen, water, and other oxidized organic and inorganic components needs to be taken into consideration, because they will scavenge and or affect the performance of the iron. And what kind of contaminants can be addressed by iron alone is pretty significant. There are many target constituents that can be treated. However, there are a few like DCA, dichloromethane, and methylene chloride, where a carbon source can aid in anaerobic biotic degradation of these compounds. And so a combined approach using ZVI with a carbon source can promote accelerated degradation. But you can see there's solvents some pesticides, heavy metals, all viable targets. So some of the reaction processes that are important to take into consideration, specifically pH, because raising pH can reduce the performance of ZVI. And with respect to oxygen, iron hydroxide precipitation is more likely to be significant in high pH conditions, as well as iron sulfide precipitation in the presence of low electrical conductivity and with high levels of sulfate. So, you know, you might get some hydrogen sulfide generation, which then reacts with the iron to have a precipitation on the surface. That may be beneficial for some compounds, target contaminants, but may not be beneficial for others. So that's something that definitely needs to be evaluated in any design process. Now, dissolved oxygen, again, leading to oxidation, and that can basically pacify the ZVI reactive surface and decrease your reactivity in a shorter period of time. So, you know, treating the water or deoxygenating the water that you're using for mixing prior to injection is really important for this factor. You don't want to start to degrade the quality of the iron or your injected media right off the bat during mixing before you even inject it, because the water wasn't prepared correctly or prepared optimally, I should say. Nitrate's important. It can result in the formation of non-conducting ferrous hydrous ferrous oxide, and then carbonate as well. There's a lot of carbonate in the water or in the groundwater, and that needs to be considered. I mean, in PRB applications over some years, that can result in a 5 to 15% decline in porosity, and also reducing the reactivity due to scaling. So some of the potential concerns for ZVI need to be considered, and this really revolves around the type of product you might select. So aggregation or clumping during the injection process is a real consideration. A lot of contractors have had different experiences with this, depending on, you know, the mixing approach, the stabilizers used, as well as the equipment. And you know, using really high pressure can sometimes magnetize the smallest particles because they're more influential. So really small, you know, nanoscale type particles can potentially have a risk of clumping and aggregation. The electrical potential of the solution is really important to monitor and can help to reduce this kind of effect, as well as understanding cation composition, sodium, calcium, potassium, magnesium, because if it falls outside of this range, or within the range of the -30 and 30, then it could cause some problems. Having zero electrical potential is actually bad. So soil pore clogging, particle size influence during injection applications. What is the geology that you're injecting into, and what are the size of the particles that you're using, and how likely is it to basically plug up pore throat spaces and reduce permeability. Soil particle interaction and reactions, depends on what the chemistry of the soil is. If there's a lot of sulfates or carbonates and things like that, that may be a concern, as well as the scaling side of things. So once it's in place and starts reacting, it starts to scale up, and so some kind of fouling may occur. Okay, so how is it done? Let's take a look at some of the kinds of questions that you would consider in the feasibility stage. First is, where do you have access? And what is the target? Is it a source or a plume? And are you going to be able to do a blanket injection, or are you limited to transects or certain areas of the site? And so that may itself dictate your overall geometry and overall objectives based on limitation to access. What product to use, how much, and how frequent. In part has to do with the first question: what's the overall geometry and what's the overall objective? What are the list of target contaminants will help you to determine if ZVI alone can work, or if it needs to be augmented with some kind of biostimulant for anaerobic bioremediation in combination. So, what are the target goals? Are there metals involved? What is the prevailing geochemistry? Touched on that already a couple times. Product longevity. Again, that gets back to, are you doing a PRB or are you doing a source area blanket-wide injection? That will dictate what your potential desirable longevity is going to be. Product distribution, are there specific stringers of sand or zones that require surgical placement? That's going to dictate particle size and some options. Also, obviously, you consider stoichiometric demand, design factor for determining a minimum level of dosage, and then stabilization options. Carbox, CMC, guar gum are two of the more common ones. And then, are there other additives required? Is pH going to be an issue? Do you need to add a buffer? Is a sand is augmenting the iron with small particle sand or silica going to be useful in a mixing or trenching type PRB application, or do you need to add EBO, so on and so forth? And bioaugmentation can also be beneficial for a number of sites. So there are different types of iron available. Typically, it's an aggregate or granular that ranges from 150 to 600 microns, which is basically a sand size. The powder ZVI, as most people might refer to it, and these are basically the particle size ranges that for iron that we offer, and through license and through direct production. This is basically a silt size. And then you have ultrafine microscale, which is generally in the 1 to 3 micron size, and that's essentially a clay. And so you can really control, when you're talking about dry powders, how much iron content you have, and some suppliers offer 90 to 94% iron, and others offer up to 99% iron. We tend to focus on the 98 to 99% range in our manufacturing specifications. But when you have an ultrafine, it generally is going to be in a solution and suspended. So there's going to be other components, liquid components, stabilizers that result in it being a lower iron content. However, because it's much more reactive, you don't need as much iron. And we can talk a little bit more about that in a bit. But nanoscale is even smaller. And, we're talking, blood cells, red blood cells, for example, are in the 8 to 12 micron range, which is in between the silt and clay. And so that's pretty small. So when we're talking nano, it's a big difference. And I'll show you an image of that shortly. So just so you can see what the spectrum of it is. For those geologists attending, you want to look at it in terms of clay, silt, sand. and I'm a geologist academically, and so that's why I referred to that in the previous slide. You can see where nanoparticles fall. This is basically what you find when you're pulling samples of clay and you mix it with water and it stays suspended for a very long time. That's what you're looking at. The microscale ZVI that's typically used in the industry is generally in the silt to sand range. And so, basically up to about 1 micron and into the hundreds of microns. So that gives you a little bit of perspective. So does size really matter? Well, that depends on who you ask, and there may be some bias involved. Ultimately, though, it depends on the objectives and or requirements to achieve specific results for performance. And that really is dependent on the geometry, the site access, and the geology of the soil is going to dictate whether you're dealing with a diffusion limited problem, or if it's a an aggressive attack approach and treating it quickly. So more often than not, we're dealing with diffusion limited problems, and so longevity does have an important consideration in the overall design aspect. And ultimately, the specific surface area relates to reactivity. And so the smaller the diameter of the particle, the more surface area you're going to have, and the more reactive. However, the smaller the particle and the more reactive, the shorter the longevity. And so let's look at that a little bit more. Some of the aspects related to available, this is kind of the one slide about the market supply or availability of iron powders. There are generally two camps, those that produce it in bulk and they're ready to ship, and the benefit is that you can basically place an order and have deliveries done pretty quickly, provided the order is small and generally speaking small, and it's already in stock. Some of the concerns for that, if it's been in stock for a while, it may have already started oxidation. Depending on the environment it's stored in, there may be some moisture issues, but it generally, people don't have 100,000 tons of anything lying around. So depending on the size of the project, you may be limited to certain quantities or particle size. And so if you're in a hurry, you are limited to what's available. But if you plan ahead, the benefits to having something made to order are that it generally is lower cost because there's no storage fees associated with taking up real estate with many tons of iron sacks. Generally speaking, it's going to be more reactive because it's not been exposed to oxidation, or not having less oxidation of the surface related to storage. You can specify the grain size and determine exactly what's going to be most optimal. So if you're actually going to do the design and say, look, I want this kind of particle size, I'm aiming for this kind of longevity, I want this kind of reactivity, a made-to-order approach may be more beneficial. The concern or the downside of it is that it could take longer, 2 to 3 months might be the case. So that's the overall difference about available options. So when we look at permeable reactive barriers, just to illustrate what we're talking about, it may be trenched, and there are ways to install them through injection methods as well. But they could be trenched or augered in, and it's granular or sand size, as we mentioned previously. I mean, they're all iron is basically looking at first order abiotic reaction. And this is assuming just 100% iron. This is a picture of the sand size or aggregate or granular iron. Here's some half-lives for different chlorinated compounds. And you're looking at 10 to 20 years, maybe an average of 15-year longevity, depending on the amount of carbonate, nitrate, sulfate, and pH, and other oxygen variables of the aquifer in which you're placing the PRB. So all of those things need to be considered, and ultimately may reduce the total longevity of the PRB, requiring either a rejuvenation and or augmenting with other amendments after a certain period of time, which becomes more of a management decision after some years. So this is an example of PRB, and it's a good example because with any PRB or even transects of injected remediation materials, you have the potential of reducing porosity permeability. That may cause the plume to move around it and widening the area of impact by not being able to control it. In this case, some kind of modification or contingency plan should be in place as part of any PRB design that may require a cutoff to make sure that bypassing doesn't occur. In terms of calculating residence time, I've provided the equation here so that you can go through some kind of evaluation and with an example, a TCE example, so that you can see how you might apply the equation. So, in some cases, in a PRB approach, it may not just be iron, and very likely could be other components, other kind of organic or other components included in order to manage some of those other chemistries that may be potentially fouling to the PRB, like carbonate or nitrate or other things like that. A powder ZVI, as typically used for injection, at least this is our particle size that we recommend for injection because it really stays within the silt size range. Some manufacturers, go up to 150 microns and say that's the size they use for injection. We prefer to stay in the smaller range. It also improves reactivity, and it still maintains a longevity of at least 5 years, and depends on how much you put in. You can increase longevity by adding more iron, probably a maximum of 10 years, and that really depends on water chemistry and what the conditions are in the aquifer, because that's kind of a higher end of what you want to hang your hat on. So the pressure that would be applied for injection really depends on the geology, depends on how narrow the interval is that you need to place the iron. And it also could depend on particle size. Let's say you are injecting into a silty sand, so you want to minimize the pressure. And in that case, you might say, look, I actually want to have something that's a 40 to 60 micron, or even a 40 to 50 micron, and that can be done. That's part of the benefit of having a made-to-order approach, that you can tailor make the product to whatever the requirements are for the site. So another option is ultra-fine microscale, which is generally less than 3 microns. On Materials makes a Zeoloid product, which does that, and it's basically clay. It's like suspended clay. If you have a clay in water you're going to have it cloudy and it's going to stay suspended or flocculated for a long time. The difference is that they have proprietary stabilizers and components that give it a shelf life of many months to a year or more. So very, very good product. And you can see the distribution of the particles. There's really no significant or material or relevant clumping of the particles, and they're all pretty small. The longevity is going to be reduced though, because there are smaller particles, and so we're looking at maybe around 3 year on the lower end, and maybe 5 or potentially more, depending on how much you add and incorporate into the matrix. But generally speaking, you're probably looking at that range. Definitely low viscosity, and very easy to inject at low pressures. Now, nanoscale, on the average, I mean, there's different manufacturers of nanoscale ZVI. We don't offer it. However, on average, it's around 100 nanometers. Pretty small. Here's a microscope, and one of the challenges with nanoscale is that it's the benefit and the challenge is that it's very reactive. So if you're looking for a really strong reactive approach, kind of like a chemical oxidation option, nanoscale could work very well. If you have a diffusion limited challenge at your site, then this may not provide the longevity that's desirable. What part of the reason why the longevity is low is that you get a lot of iron oxide precipitation on the surface of those very small particles, and that basically pacifies the reactivity and renders it less reactive to non-reactive. And it takes some time, months, but it does occur. And generally speaking, it's definitely less than a year. There are different additives and components that people are adding to it to try to improve that, but generally speaking, it's a short time period. So how do you design or calculate the quantity of ZVI required? So here are some basic components of that process of calculating it. So you want to look at hydrogen demand for your target contaminants, and combine that with the demand for multiply the demand of hydrogen by the specific hydrogen capacity of the ZVI, and then multiply that by the theoretical demand of the site-specific design factor, which is basically your fudge factor, your best estimate as to how challenging it's going to be. And that's where you start looking at what other geochemical parameters, pH, DO, sulfate, nitrate, carbonate, and all of those kinds of variables. Other scavengers like metals and so on and so forth. So you can come to your calculation, and that's going to give you what I would say is your minimum, because while it's always important to have a very detailed conceptual site model, sometimes budgets don't allow the level of detail that a designer would prefer. And so there's going to be some level of unknowns, data gaps, or lack of confidence in some of those components and calculations. And so that's where the design factor comes into play. But more often than not, people use anywhere between a 0.25 to 1% by weight for source areas, and even more than 1% by weight for PRBs. But and that's because you're relying more on residence time in the case of a PRB, it's pretty critical. And so you will need, you need to have more in general, more iron. So assessing the quantity estimated that can be injected gets into what are you stabilizing it or you know, putting it into solution with, and what is the volume. So if the required slurry volume is less than 15% of the total porosity in the treatment zone, the quantity can be injected. If more than 15%, then you might break it up into multiple injection events. And of course, this is really dependent on the geology. So you might want to do a pilot study to evaluate what that site may be able to receive in a single application as opposed to a multiple injection event application. There are benefits to having multiple events because then you can stagger the injection point locations if it's temporary points, and that gives you better distribution overall to achieve the same volume for the demand that's been calculated or determined. And then if the volume is less than 10% of pore volume, the volume of material, the slurry volume, is less than 10% of pore volume, then you can just dilute it and inject it at a 10% of the pore volume. So these are some general guidelines. Again, you really need to look at the site-specific details and incorporate all the different variables and aspects to make an informed decision. So some of the key planning and application considerations are geometry and overall schedule and approach. Is it a single or multiple event? And you know, what tooling are you going to use? Direct push, permanent injection wells, high pressure fracturing with pneumatic and hydraulic fracturing, or pressure pulse technology, and there's others, soil blending, ex-situ or in-situ, and then emplacement. So those are important variables to consider, because depending on how you plan to implement or what you're limited in terms of site access or implementation, the mixing approach may dictate that you know, a lower cost coarser material is going to be just as good as a highly reactive smaller particle. So you know, there's no hard and fast rule about applying ZVI. You really need to incorporate all the different components because they all relate back to each other if you're going to look at optimizing and minimizing costs while optimizing the performance, which is, you know, seeking the most value. Radius of influence and number of injection points, again, that depends on depth. You may have a very large vertical interval, and so therefore you may have to have multiple event injection anyways. One that is involves fewer points for the deeper zone, and one with more points in the shallower zone, and then you can divvy up the volume accordingly based on that geometry of injection points. And you know, generally speaking, how you go about doing that is, I think, a very individual decision. Using a spreadsheet to model it and do some kind of sensitivity analysis could be helpful in going through that evaluation. So key implementation considerations are, what is your stabilizer suspension media? Again, carboxymethylcellulose, guar gum are two of the more common ones. And there are others and other components that are added. And actually you can mix the CMC with the guar gum, and there are studies to show that under certain conditions that is more optimal, both in terms of suspension longevity for larger radius of influence distribution, as well as reduced viscosity to improve the rheology for further achieving a larger radius of influence. So that's something to look into, because that's an important component of the entire injection process, not just the iron. Mixing and pump requirements, injection spacing, verification of distribution is also really key, and this is where maybe doing a pilot study in advance could be very beneficial. Here's an example of some low pressure equipment, complements of on materials, and you can see that generally speaking, the amendments are commonly injected through injection wells or existing monitoring wells, because the particles are clay size, so moves under relatively low pressure, moves pretty easily through, or in temporary injection points. If we look at intergranular, the difference between intergranular semi-homogeneous distribution versus high pressure fracturing, you're going to get different rates of influence dependent on the amount of silt and fines, this being a clay, this being a sand, and this being a silty sand. So, there's slight variations in both the geology and the influence of the hydrostatic pressure. But if you look at, how does that compare to fracturing? The fracturing doesn't change all that much in terms of distribution. However, you're more likely to get a better web through coarser sand materials than you might through a clay. And so when you look at in-situ applications, options, source area treatment, it's more of a grid versus a PRB, or even a modified plume treatment approach using transects can be very beneficial. Radius of influence verification should be done, or is recommended to be done during a pilot, and you might choose a location to inject 2, 3, 4, 5 points in order to achieve specific performance criteria results after verifying visually in fractures, the fractures in soil cores, or the distribution if you use a small particle nano or ultrafine. You'd want to look at magnetic separation, use magnetic separation with ZVI from soil cores. You can look at ground deformation, but more often you're going to be looking at groundwater indicator parameters. If it most likely it's a groundwater treatment approach, so you can look at geochemical parameters, total iron content, iron and total organic content, and or PDO, temperature, pH, all of those variables, and you want to monitor those things because you want to see how pH and those variables are going to change post-injection, and see if any kind of modification is going to be required for the full scale, including amendments, buffering, or modifying the ZVI or adding to the ZVI to mitigate certain undesirable outcomes based on background geochemistry. So that pretty much summarizes the introductory level discussion. I think there was enough information about the different types of materials available, the different considerations, and of course everything's site specific. If more likely we're going to do something again later this year that involves components and introductory information from different injection providers, as well as trenching and other contractors, to discuss the different techniques and their main differences and how you might incorporate that into your overall design, the combination of bio with ZVI, and review case studies and lessons learned. I think that might be a good next step for the next webinar on ZVI and in-situ chemical reduction. There's a couple of reference documents that you might want to Google or search online for and download and take a look if you want to do a little bit more reading. There was a 2015 I think it was 2004 PRB, ITRC PRB study that I was one of the group members on. And I wasn't part of this more recent one, but this more recent one actually builds on the prior one, and it's a pretty good reference. So I highly recommend both of those. And here's my information. If you needed to reach out to me, I think we'll open it up to questions now. And feel free to use the Q&A button to enter any questions you have. So one of the first questions is, what is considered high levels of pH and nitrate? Well, pH above 8 is going to start looking like a problem. And so if you're already at that, you really want to look at maybe doing a bench study with site materials and or a treatability study. The amount of nitrate, it's a good question. I'll have to get back to you on that. I don't have that up ready off the top of my head. The next question is, how does one select a specific particle size range for an application? And again, that really is going to be reliant on your geometry. What's the overall objective? If you're looking at a source area treatment, more often than not in a blanket wide injection, so you're getting maximum distribution to treat all of the contaminants quickly, a smaller particle size may be more desirable. If there's a lot of silt or clay, there may be diffusion issues, so then you start thinking about, well, if diffusion's part of the factor, I need something that lasts more than a year. So larger particle size, slightly larger, may be more beneficial to provide that kind of longer term management. If you're looking at transects or PRB type installations where longevity is key because you have to wait for diffusion to occur and then for those contaminants to migrate to the point of interaction or reaction with the PRB, then more longevity is going to be required, so even yet larger particle size. Going through a bench study, and bench studies aren't that expensive for iron. You can select do a calculation for demand, consider your injection approach, the geometry, and then evaluate a couple of different size distributions or more specific size materials, considering both the geology part of, the soil type that you're injecting into, as well as potential preferential pathways, and coarser sand stringers or intervals, and then also your injection approach or your in-placement approach. If it's not injecting, if you're in a part of the world that doesn't offer the type of sophisticated injection equipment that many of us are spoiled with in the US, then more rudimentary in-placement options are going to be required, and then that may dictate certain options in terms of particle size and composition. So there's no simple answer to that question. It's a good question, but not a simple answer to it. Any other questions? Please put them in now, because we're getting to the top of the hour and we'll be ending soon. Another question is, ZVI could be used for remediation of heavy metals in mining, dams, and which size? Again, that really depends on the application. In mining, you may have tailings dams which require dewatering, so a coarser iron could be used in water treatment. But if there's going to be mixing, basically superficial mixing, again, it could be a coarser material, or a finer material, depending on how reactive and how quick you want things to take place. If it's a PRB style, then could more likely all the options are a consideration. It really depends on what metals are the target and what the sulfate levels are, nitrate, carbonate, as well as the variety of different metals there. pH is going to be very significant. So heavy metals is actually an area of expertise of ours, and so we can be happy to speak with you directly if you have any more specific information about what challenges you might be faced with. All right, last question. Oh, it's just a note. All right, well, thanks a lot, everyone. If you have any more questions, please send us an email, and we'll be happy to help you with your evaluation. If you have any questions about the content or the presentation, feel free to let me know. The recording will be made available as soon as possible, and all registered attendees will receive an invitation to access the website where the recording will be available on an as-needed basis. And eventually it will be placed on the EnviroExpert.net website, and so that'll be open to the public at that time. But that may be a little while. We'll at least send you a link to watch it on a private page. Thank you very much, and wish you all a great day or evening, depending on where you are in the world. Bye-bye.